Welcome to the Nick Bryant podcast. I realize that many of my listeners and viewers like my work on the darkest recesses of humanity. But as my podcast has grown, I've started incorporating various interests of mine, like psychology and anthropology. And today we have physicist Eric Gutman to talk about physics. Eric graduated from the University of Chicago with a master's degree in physics. How you doing today, Eric?
I'm fine, thank you.
So we're going to kind of take a long and winding road along modern physics. And when I think of the Big Bang of modern physics, I think of Albert Einstein. And Albert Einstein had a very interesting background. When World War I broke out, he went to Switzerland to avoid the draft. He was very much a pacifist. And he eventually graduated from the Swiss Polytechnic Institute, and he could not get a job. Albert Einstein could not get a job after he graduated from college, and he thought about becoming an insurance salesman. Could you imagine knocking on the door and having Albert Einstein there to sell you insurance? But he ultimately got a job as a clerk at the Swiss Patent Office. And that's where he came up with some of his most revolutionary ideas. And Eric, why don't you fill us in a little bit about Einstein's background too?
Yeah, you said it very well. First of all, imagine Albert Einstein knocking on the door selling you insurance. He was very talented, very gifted in certain ways. By his own admission, less so in others. Although he became a very successful young physicist, particularly with his work in grounding motion, special relativity, later on general relativity. By his own admission, he quote unquote failed miserably in marriage twice, and I know that's something you want to get into later. So he was a man who had very strong strengths and who also had some weaknesses that many others share.
So with Einstein, he's working as a patent clerk, and I think he patent clerk grade 2. And then in 1905, he revolutionizes physics. He comes out with a paper that proves the existence of a photon. Photon had been thought to be waves at that point, not particles. And then he proves the existence of atoms, and the existence of atoms was still in a very nascent nebulous state. And then he comes out with special relativity, E equals mc squared. And give us a rundown about special relativity, Eric.
Sure. I'm not sure I would assign all of those accomplishments to Einstein, particularly with the the existence of different parts of the atom and so forth. But special relativity is undeniably his work. And E equals mc squared is obviously the most famous result of it, that demonstrates how a couple of things. One, how mass and energy are easily exchangeable, how one is easily converted into the other, and the enormous amount of energy that can come from a relatively small amount of mass, which essentially has changed the course of human history. Because if you can find an isotope that can be easily broken apart, or that can be possible, let's not say easily, possibly broken apart, and turned into energy, well, the amount of energy that will be released is enormous. It's equal to the mass times the speed of light squared. And that was the impetus for Albert Einstein writing to FDR, telling him that an atomic bomb could be made, would be a very effective weapon, even though he was a pacifist. You're correct. And he remained a pacifist even after World War II. He felt that there was no other choice, but he was absolutely a pacifist throughout his entire life. And of course, atomic bombs led to nuclear weapons. And so E equals mc squared essentially changed the course of history.
And he worked out E equals MC squared with algebra. He didn't use calculus. It's kind of amazing. I don't know if mathematics was Einstein's strongest suit, but this cup right here probably weighs 10 grams times the speed of light squared. That's how much energy it has in it. So this cup could blow up the entire East Coast if all that energy was harnessed. It's quite remarkable.
It is actually very remarkable. And Einstein, excuse me, you are absolutely correct in that special relativity is derived using algebra. There's no calculus in it. It's derived using algebra, and there are many other very fascinating results that come from it. For example, before special relativity, there was a misnomer that we existed in some ether throughout the universe, some ether that was proven to be false. We also obtained the speed limit of the universe, which is the speed of light. Nothing can go faster than the speed of light. It is the universal speed limit. And from there, you derive all kinds of very interesting phenomena. Newtonian physics remains approximately correct unless we start moving at speeds close to the speed of light, in which case our masses as measured by each other begin to approach infinity. The time the way we measure time begins to slow down to zero, and even length contracts. A pole moving close to the speed of light can fit into a room that it otherwise would not be able to fit into. So we start getting very, very interesting science, even in special relativity, which, as you correctly pointed out, is derived using algebra.
What's interesting about special relativity is you've got the twin paradox. The closer you get to the speed of light, the more time slows down. So if two twins were born and one stayed on Earth and one traveled near the speed of light for 60 years, he would come back more or less as an infant, and his brother would be an old guy like me. That's what's kind of fascinating. And with the speed limit, if this cup was approaching the speed of light and actually attained the speed of light, it would cease to exist. It would become pure energy. That's another built-in component of special relativity.
Yeah, that paradox is a very famous one. And it would not seem like 60 years to the twin who's on board the rocket ship. It would seem like only minutes. And then that twin would return to Earth, and that twin's sibling would have aged however many years, depending on how fast the twin on the rocket ship was traveling. So yeah, you start getting into very interesting phenomena.
So Einstein published these three, or actually four papers in 1905 that revolutionized everything, but nothing happened. He was very fortunate. Max Planck, who was he was German and he was the editor of the Annals of Physics, published these papers because Planck was ahead of most people as far as quantum and atoms and things like that. So he saw Einstein's genius, but no one else did.
Well, Einstein's genius had to be forced upon many physicists in the world during that era. He was famously or infamously not a Nobel Prize for being Jewish until it became the elephant in the room at nearly every physics conference. And those the powers that be realized that they had to give it to him sooner or later.
Well, here's a guy that's a patent clerk that's not even working at a college, that can't get a job at a college, and he's sending these papers to Max Planck, and they're revolutionizing physics, and people just didn't want to overturn 400 years of Newtonian physics. And I also believe that it overturns Euclidean physics, but we can get into that a little bit later. But Einstein, he's a lusty guy. People think of him as like this old dried up codger, but actually he was married, he had two children, and then he got an academic appointment in Germany, and he fell in love and married his first cousin. So this is Albert Einstein. This is in Appalachia and the Hatfields and McCoys. Albert Einstein married his first cousin. Why don't you riff on that a little bit?
Yeah. So as I said earlier, you know, Einstein was very self-aware of both his strengths and his weaknesses, which happens to be a very important character trait, in my opinion. He knew his strengths, he knew his weaknesses, and he very readily admitted later in life that he had failed dismally in marriage twice. Even after marrying his first cousin, they slept in separate bedrooms. He was just not, perhaps he had lust, as you said, perhaps he lusted at, he lusted after females, but his head was in a very different space. It was in a very different space. I also want to comment on something that you said that's actually very important. And you said people were reluctant to overturn Newtonian physics. And that is absolutely true. When you have a theory or a set of theories that have been in existence for so many years, hundreds of years, and experimentally, they've been confirmed. Now, as we know now, experimentally, Newtonian physics was confirmed at velocities not close to the speed of light, which is why they were approximately correct. But when you have confirmed theory for so long, for so many centuries, nobody really wants to overturn it. And someone very foolishly said in 1900, I believe it was, perhaps a few years earlier, that all we have left to solve in the world of theoretical physics, in the field of theoretical physics, is the photoelectric effect. That's all we have left to explain. And then theoretical physics will be done. 1905, special relativity came out and turned everything on its head.
With Einstein, so he married a fellow physics student, but she could not pass the test at the Polytechnic Institute. And they had two children, but Einstein was not a very good husband to her. And he wasn't, I don't think, a very good father. And he ultimately he started corresponding with his first cousin. And he told his first cousin, this was before he moved to Germany, but he'd been to Germany a number of times for lectures. But he told his first cousin that it was getting too complex. So I guess an affair was getting too complex for even Albert Einstein. But then his wife did not want to give him a divorce. But he said to her, I'm going to win the Nobel Prize at some point, and I will give you all the money from the Nobel Prize if you give me a divorce. And then, so that was it. She gave him a divorce, and he won a Nobel Prize for photons, not for relativity. And he went to live with his first cousin, who he had affairs on. It was no one would think this about Albert Einstein, that he was a lusty guy, but that's the way it was.
But just to clarify a point, so Einstein had a few great accomplishments. Brownian motion was probably the first, and then special relativity, and then general relativity. He didn't win the Nobel Prize for any particular accomplishment. The more he accomplished over time, the more pressure began to build to award him a Nobel Prize, until finally it had to be given to him, essentially, to get rid of the elephant in the room. And so I believe the exact wording was or to paraphrase, actually, for contributions to theoretical physics and so forth. So it actually was given for a variety of contributions.
So after Einstein accomplished those miracle papers in 1905, he really took on a monstrosity called general relativity. And general relativity, when physicists talk about space-time, it's just like, that's just the way it is. But actually, before Einstein, there was no space-time. Einstein, with his general relativity, showed that space and time are bent. And it couldn't be proven And Einstein was thinking of ways, how can I prove this? How can I prove this? Because none of his theories had been proven at this point. And he figured, I can do this through an eclipse. I can show how the sun bends stars, the light of stars during an eclipse. And he predicted the stars that would be bent that you generally couldn't see. And there was two researchers that went to to an eclipse in the Crimea, but the First World War had started, so both of them got arrested and their photographic equipment was taken. Finally, it was a guy named Eddington, and in South Africa in 1919, there was a full eclipse, and exactly what Einstein said happened, that you were able to see stars that you otherwise wouldn't be able to see because gravity is bending their light. And that was really when Einstein.
Gravity is bending the space time.
Yes.
Well, actually, gravity is the bending of the space time, but the masses in outer space are bending the space time through which the light is traveling.
But because there's no straight lines in nature, because gravity bends everything, it even overturned general relativity, even overturned Euclidean geometry, which we had been using for 2,000 years. Now, Euclidean geometry is feasible in a vacuum, but without gravity. But I don't believe it's correct because of general relativity. What do you think about that, Eric?
Okay, so just clarify a few things for for your audience. So the connection between general relativity and special relativity. Special relativity is a simple case of general relativity. And that is why it's so simple, in fact, that it can be derived using algebra. Here's how special relativity fits into general relativity. Relativity postulates that the universe is a four-dimensional map, almost like a fabric of space-time. Three spatial dimensions, temporal dimension, a four-dimensional manifold of space-time. Now, that manifold, that fabric of space-time, curves in the presence of mass or energy. And in fact, mass and energy are essentially the same thing from the perspective of relativity. We even refer to it as mass energy. They're essentially the same thing. Because as we were talking about earlier, the one can be converted into the other very, very easily through E equals mc squared. So in the presence of mass energy, the fabric of space-time, the four-dimensional manifold of space-time, curves. Now, special relativity is the special case in which there is no mass energy. It is where the universe is flat. And in most of outer space is empty. Space is mostly empty. Okay. Yeah, you have hydrogen here and there, the cosmic microwave background. But most of space is empty. And in those areas, not perfectly empty, but approximately empty. And then, so in those areas, special relativity is a very good approximation because space-time is not curved unless you have mass or energy. Now, when you do have mass or energy, space-time does curve. That four-dimensional manifold of space-time does curve. And that curvature is what we call gravity. Gravity is the curvature of space-time in the presence of mass energy. So there are four fundamental forces, as we learned in high school physics: gravity, the gravitational force, the electromagnetic force, the strong force, and the weak force. Well, of those four forces, gravity is unique because it doesn't operate the way the other forces do. It's more a property of the four-dimensional manifold of space-time. It's property of curvature in the presence of mass or energy. A black
Let's back up 1 second. I just want to say, so
hole.
there's four forces that we know of in the universe. The first force is the strong force, which keeps the atom together because positively charged protons should not stay together. The weak force works with inside the atom and actually changes various subatomic particles. The third force is electromagnetism, and the fourth force is gravity. So you can pick up from there, Eric, if you could.
Sure, absolutely. So a black hole, which I know fascinates people everywhere, is a black hole is caused by the presence of so much mass in a volume of space, a mass that is so dense in a volume of space that space time, the very fabric of space time, curves so much that it becomes warped. And there is no trajectory, what we call a world line, that's the technical term. There is no trajectory out. There is no way to escape. Once one gets within a certain radius, known as the event horizon, of that black hole, the four-dimensional fabric of space-time is so curved, it's so warped like a pimple that there's no way out for even photons, for even light. And so that is how a black hole is postulated by general relativity. Interestingly enough, general relativity, through what's known as the Schwarzschild metric. The Schwarzschild metric is essentially the graph of four-dimensional space-time. Mathematically, it actually predicts a white hole, a hole where everything gets pushed out. It also predicts the famous wormhole, which we've been trying to find in outer space to try to travel very quickly between different regions, vast regions of outer space. Neither one of those has been found in nature. Neither one of those has been found in nature. In terms of Euclidean geometry, this is important to clarify. Euclidean geometry has not been overturned. Euclidean geometry is perfectly valid. It is valid it is applicable in many areas, including a flat surface. And as we know, the shortest distance between 2 points on a flat surface is a straight line. That is actually how airplanes work. However, in general relativity, we're no longer dealing with perfectly flat space because there is mass throughout the universe. There is energy throughout the universe. So we're no longer dealing with perfectly flat space. So the shortest distance between 2 points, which affects gravitational attraction and so forth, is no longer described by a flat line. It's described by what is known as a geodesic. A geodesic is the shortest distance between 2 points on a curved surface. So it's not that Euclidean geometry is overturned or not true. It's just that it can no longer describe many of the physical phenomena in a curved metric of spacetime.
Einstein was a firm believer in everything is one. And he tried the four forces that we're talking about. He tried to unify those four forces: the strong force, the weak force, the electromagnetic force, and the gravitational force, because that's what he worked on in, I don't know, the last 20 years of his life, is those, trying to unify those forces, because he firmly believed that everything was one. Spinoza was his favorite philosopher, and Spinoza is the rationalist that postulated that everything is one. And actually, there are a number of Eastern schools that postulate that everything is one. And actually, the strong force, the weak force, and the electromagnetic force have been unified, but not the gravitational force. Why can't we do that?
So a few things there. One, you're absolutely correct. Einstein spent the last decades of his life looking for what is known as a unified field theory. which we're still looking for to this day. Because to a physicist, it's not enough to be told that this is the way it is. We want to know why. And once we're told why, well, okay, well, why is that true? And why is that true? And why is that true? We also have many constants in the universe, many constants, the permittivity of free space, and so forth. The just too many to enumerate here. Why do those constants have values that they have? The gravitational constant. Why do they have the values that they have? Why? So ultimately, in an ideal world, we would want a unified field theory that explains everything. So nothing is just left out in the open. Why is this true? Why is that true? Why is this constant that? And so on and so forth. That has not even been close to being found yet thus far. So I was searching for that, and we continue to do so today.
Why can't gravity be unified with the other three forces? The other three forces are unified. But yes. Why can't gravity be unified?
Gravity is a different sort of a force, and I was alluding to this earlier. Because in a sense, it's not really a force. It's a property of space-time. It is the curve. I remember physics 1 when I was in college. Our professor purposely decided to throw a factoid at us that we would not understand. And out of nowhere, said that gravity is the curvature of space-time. None of us understood it until a year of modern physics. But gravity is not a force like the other three forces. Property of the fabric of space-time. It is the way, the curvature of that fabric in the presence of mass or energy. So else, atoms and the forces that go with them, and charged particles, which obey the laws of the electromagnetic force. All of those particles and the forces that them are within the four-dimensional metric of space-time. They're matter in the universe. But gravity is a property of the universe itself. It's the way the universe moves in the presence of mass.
So others have tried to unify. Gravity is the force that keeps everything together. It creates black holes. It keeps the planets going around the sun. Gravity is a huge player. I mean, without the other three forces, you don't have the universe, but gravity is a huge player. Do you ever foresee gravity getting unified with the strong force, the weak force, and the electromagnetic force? Is that even a possibility?
It's interesting. Of the four, of the four forces, and again, when I refer to gravity force, I do so out of tradition. But again, as I've been very clear that it's not the other three. And when comparing the four forces, gravity is actually the weakest one. It is the weakest one. Yet it really does shape the universe. I'm not sure or shape galaxies and so forth. I'm not sure I would, excuse me, I'm not sure I would phrase it quite the way you did. It does shape galactic systems. It shapes solar systems. It shapes planet. It shapes everything. Why? Well, the electromagnetic force cancels itself out. A positive charge does a negative charge. Cancels itself out. There are no monopoles. So there goes that one. And
what do you mean by that? That electromagnetic force cancels itself out.
For every positive charge, there's a negative charge. For every negative charge, there's a positive charge. So they end up canceling each other out. They don't shape. The electromagnetic force does not shape galaxies. It does not shape solar systems. Gravity, which is a much weaker force, does. There's nothing to cancel it out. And again, it's a curvature, but it is interesting that a stronger force, the electromagnetic force, cancels itself out between its positive and negative charges. The strong force and the weak force only come into play in very small volumes. We're talking about very small distances. So what is left to shape galaxies? Anything they contain. And other objects, other celestial objects. Gravity.
But if wasn't a strong force and a weak force, there wouldn't be any atoms.
Right. We're not saying that, as you said, it's not like the other three forces are optional for the universe to be as we know it. It's just interesting that the weakest force of the four is the one that shapes galaxies and everything they contain.
What's interesting for me, we talk about the Big Bang, and there was researchers that were looking at supernovas, and they were measuring the speed at which supernovas were, because everything in the universe is expanding. We know that. And they found that these supernovas were expanding at a much higher velocity than what Einstein had predicted. What's up with that? I mean, and all of a sudden dark energy gets introduced, that, and it's the variable that is causing the universe to expand at a much rapid fashion than it should. What is black energy?
Dark energy. So dark energy, as opposed to dark matter, which is what I studied in graduate school, or which is what I wrote my thesis on in graduate school. Dark energy is the driving force of universal expansion. Excuse me. In other words, dark energy was discovered by Michael Turner at my alma mater, the University of Chicago, is the driver behind the expansion of the universe. It is what pushes the expansion of the universe, dark energy. You don't see it, hence it is called dark, but it drives that expansion. Now, that expansion of the universe is not the way one might instinctively imagine it. The universe is not expanding like a room that has walls being pushed back. It's expanding from the inside. Let me just explain what that means for your audience. Volume, even volume of space, comes in little pieces. Or the way a physicist would say it, volume is quantized. Comes in little pieces. And each little piece of volume is growing, is expanding. So hypothetically, if you were to be sitting at your computer for the next 10 years, the distance between you and your computer will have grown, because the little pieces of volume between you and your computer are all expanding. That is what we mean when we say the universe is expanding from the inside. So the farther away an object is from you to start, the farther away it's moving. Why? Because you have more little bits and pieces of volume, of universe, if you will, that are all expanding. So the farther something is away to start, the more bits and pieces you have in between that are expanding, so the faster it's moving away even more. And that is what we call redshift. And redshift is how we determine the distance between the Earth and very distant objects in space.
When an object is moving towards someone, it has a blue shift, and when it's moving away, it has a red shift.
Yes.
So do we have equations for dark energy? It's kind of a enigmatic thing to me. What can you say about the existence of dark energy and whether or not we have equations that account for dark energy?
Absolutely. Everything we have been discussing on this call is mathematically derived. Everything, literally everything. A workup would be to go back to the beginning and to build up, and that is what people spend years in graduate school doing who study it. So to get into a quantitative thing would be a much more involved conversation. But there is a mathematical workup to all of it. And it's important to note that all of these discoveries, all of these fascinating discoveries, counterintuitive discoveries, were all derived mathematically. They were all inferred mathematically. We say there's the observable universe and the universe that can be inferred. Most of our theoretical physics is not from direct observation. Most of it is from inference. It's from inference, and there has behind all of it, including dark energy. Just to briefly touch on blue shift, just to explain that to your listeners. So blue shift and red shift. So how can we determine how far away an object is? Well, if an object is moving away from us, just due to the fact that it's moving on its own, or whether it's due to universal expansion, the universe expanding, if an object's moving away from us, the light that is bouncing off of that object is still coming towards us, but at a reduced frequency because that object's moving away. It's almost as if someone is running back away from you while throwing you a tennis ball. It reduces the velocity of the tennis ball. They're moving because they're moving away as they are throwing the ball. So in the case of light, which travels as a wave, the frequency of it is going to go down because the emitter of the light is moving away as it's emitting the light. Hence, the frequency goes down. The frequency of the waves that are hitting us goes down, and so there's a shift towards the red end of the spectrum. Blue shift is the exact opposite. An object's coming towards us. Well, then the frequency of the waves hitting us is going up, and there's a shift towards the blue end of the visible spectrum.
I've got a question.
Sure.
So ultimately, it's the mass in the universe that determines how large the universe is. It's all encompassed. The universe is encompassed in its mass. It's gravity. So what would be on the other side of let's say that you've got that you go to the very end of the universe where as far as gravity will take you, what would be on the other side of the gravity? Do we have any idea?
So just to clarify, it's dark energy that determines the expansion of the universe, not mass.
Okay.
But if you were to go to like the walls of the universe, if you will, well, I'm putting aside the fact that they cannot be reached by Earth because they're already so distant from us. They're so distant that there's so much volume between us and the end of the universe, if you will, that it's moving away. Because remember, the farther away an object is to start, the more quickly it moves away from us. So they're already so distant. There are regions of the universe that are moving away from us faster than the speed of light. And people are like, I don't understand. You can't move faster than the speed of light. Because it's not an object moving. It is simply the rate at which that object, the volume between us and that object is growing. It's not the object moving. So putting all of that aside, even, what's on the other side of it? Nothing. There is no other side of it. There are a few different theories, by the way, as to the shape of the universe. A few different theories as to the shape of the universe. Even incorporating the fact that the universe curves in the presence of mass or energy. There's a theory that the universe, taking out mass or energy, just going back to special relativity without mass or energy. There's a theory that the universe is flat. There's a theory that the universe is spherical, and there's a theory that the universe is hyperbolic. So it has yet, and obviously, good luck trying to experimentally confirm that. I'm not saying it can't be done, but nobody has done it yet.
So let's get into quantum mechanics. Einstein had a hard time with quantum mechanics because he liked laws, and quantum mechanics doesn't adhere to special relativity or general relativity most of the time. And it's what's interesting to me is when quantum mechanics started to happen, it was in the 1900s, like 1911, I think it was, that Niels Bohr and Ernest Rutherford at the Cavendish laboratory kind of were figuring out quantum mechanics. And then you had a kind of a quantum leap, pun intended, with Schrodinger and his thoughts about quantum mechanics. Can you explain that a little bit to us?
So quantum mechanics is one of those areas of physics that I think people like because of the name quantum. It's excuse me, it's not easily understood and it's not easily explained. The math is very intense. And by the way, before I forget, you mentioned Einstein's math skills. As the lore goes, Einstein failed eighth grade geometry. But general relativity uses what is known as differential geometry, which is 100 times harder. Excuse me, which is 100 times harder. And Einstein mastered it. In fact, Einstein, regardless of whatever happened in the eighth grade, was a master of advanced math, which is used in relativity, the math of general relativity, as opposed to special relativity, which is done using algebra. The math of general relativity is very, very intense. For vector notation and differential geometry and so forth. So yeah, a lot of his work really relied on his math prowess, was a result of his math prowess. In terms of quantum, so quantum physics is what chemistry is really predicated upon. For your listenership, remember high school chemistry? That is simplified quantum physics. Quantum physics tends to come into play on a very small scale. It involves waves and the behavior of waves in an atom, in a nucleus. The word quantum actually means a quantum, and same etymology, same root. Earlier I said that volume is quantized. Well, energy was the first to be discovered as quantized. A quantum is a quantity of energy, a packet of energy, if you will, which is equal to Planck's constant, h, times its frequency.
And kind of break down Planck's constant for us a little bit.
Well, Planck's constant, I mean, it's a constant. Breaking it down is kind of going on the way to the unified field theory. It can be experimentally confirmed, and it's the result of Planck's constant and multiplying it by the frequency of a photon, get the photon's energy, is that energy cannot exist in any amount. It is quantized. It can only exist in certain quantities, and those quantities, the energy of any photon, which is a photon is a particle of light. So the energy in any particle of light has to be equal to Planck's constant times the frequency. It cannot be anything. It has to be in certain levels, certain energy levels, which is where we start getting the energy levels of an atom from, and lots of things can be derived from that. So that's kind of like the starting point. And then once you start getting into the wave equation, Schrodinger's wave equation, we start describing a probabilistic distribution. Again, I don't want to lose your audience here. A probabilistic distribution of where subatomic particles can be found in three-dimensional space at a given time. That is and interestingly enough, Einstein always referred to it. He was very mathematical. He didn't refer to it as the wave equation. He referred to it as the psi function. We use the Greek letter psi to denote the wave equation. But it is a description. Everything comes from quantizing energy, but it is a description of the probabilistic distribution, the probabilities of finding subatomic particles at a given region of space at a particular time. Because again, when you have like the cloud model of which is really what the accepted model nowadays, the electron cloud model of an atom, well, all you have for any given electron is a cloud, it's a probabilistic cloud. How do you know where it is inside of that cloud? How do you know? Well, the answer is you don't. But you have a probabilistic distribution that is described by the wave function. And of course, there is uncertainty, and that's where the uncertainty principle comes in.
And Einstein had a lot of problems with certain facets of quantum mechanics. Quantum entanglement is kind of an interesting concept. It's two particles can drift apart. They can be apart for thousands of miles, but if one moves left, the other one will move left. If one moves right, the other one will move right. They're somehow connected. And Einstein, that made no sense to him because he didn't understand what kind of forces would be at play with quantum entanglement.
Well, Einstein's primary objection to quantum was a philosophical one, if not a religious one. He was religious for only a couple of years in his early 20s. After that, he became quite secular, but he still maintained strong belief in God. Now, his conceptualization of God might be different from that of others, but he had a very strong belief that there was an intelligent being that was designing the universe, that had designed the universe. And Einstein very famously said that God does not play dice with the universe when he initially rejected quantum. So his rejection was on philosophical and religious grounds, and they might have extended beyond that into quantum entanglement and other resultant concepts. Now, moving on to quantum entanglement, when you have
let me just ask you this real quick: what were the Einstein's major philosophic disagreements with quantum, other than quantum entanglement?
Well, quantum entanglement was not his main disagreement. It could have been just a resultant, rejection, because he was rejecting, quantum as a whole. Like I said, his main rejection of quantum was a philosophical one. He felt the more Einstein, and this goes out to all, I guess, the atheists out there, the more Einstein learned about the universe and discovered about the universe, the more a firm believer in God he became. Now, again, the way he conceptualized God might not be the same as the way other people do. But the stronger a believer he became that there was an intelligent being behind the construction of the universe. He felt it was too perfect otherwise. He did not feel initially, then he later realized that he was wrong. But initially, he did not see quantum as fitting into that. He felt that God did not play dice with the universe because ultimately there are unanswered questions from quantum. If you have a probabilistic distribution of the location of a subatomic particle in three-dimensional space as a function of time, all you have is a probabilistic distribution. Really, that particle can be found anywhere in its orbital. It can be found anywhere in a three-dimensional cloud, yet somehow it goes in one direction as opposed to another. How? So
it's
the way Einstein wanted to see the universe.
It's the uncertainty of quantum mechanics that really troubled Einstein. He thought that you had definitive laws, that God did not play dice with the universe, and quantum isn't working out to be as a definitive law. There's too much uncertainty, too much improbability.
Well put. Well put. That is why he initially, and yeah, later on he realized that he was wrong, but that is why he initially rejected it.
And my second favorite equation after E equals mc squared is Dirac's equation, because quantum and relativity could not be squared. They just were highly incompatible. But there was a physicist named Paul Dirac, who most people have never heard of. And he used the principles of Schrodinger and other people that had been instrumental in developing quantum. And he had an electron going near the speed of light. So he was combining both quantum mechanics and relativity. And he predicted, and the guy just figured this out with a pencil and paper. I don't understand it, but he predicted antimatter. And antimatter was science fiction up until that point. And actually, it took some years after the Dirac equation before we even discovered antimatter.
A few things. One, Dirac. Actually, even before Dirac. So you've mentioned E equals mc squared a few times. And as I said, the consequences of it cannot be overstated. The way they impacted human history, especially in the past 100 or so years. However, within the larger framework of general relativity, perhaps Einstein's greatest accomplishment was the Einstein curvature tensor. So it is, I do want to point out that Einstein's greatest achievement, certainly in the framework of general relativity, is the Einstein curvature tensor, which is what describes the way the four-dimensional fabric of space-time curves in the presence of mass and energy. That is perhaps even a greater achievement scientifically than E equals mc squared. Although E equals mc squared, as already stated, has had a huge impact on human history over the past 100 years. In terms with regards to Dirac and antimatter, it caused a huge stir. In fact, the lore goes that Dirac was initially refused his PhD because he mocked incessantly over his concepts of antimatter. It was looked upon as being utterly ridiculous. People were not buying it, and he was not going to be awarded his PhD when, interestingly enough, Einstein intervened and told his advisors that he should be awarded his PhD. And Dirac was correct. Dirac was correct. There is antimatter.
And we use antimatter every day with PET scans. We're using positrons.
Yeah, so this gets into the realm of particle physics. Antimatter is also created naturally. It's created naturally by the collisions of particles. And so destroyed naturally. So you have a constant cycle. The same way you have a water carbon cycle, you have a constant cycle of matter and antimatter annihilating each other, the one being created, the other being created, and then annihilating each other again, and creating energy constantly in the realm of particle physics. Every moment of time, you constantly have interactions like this. Absolutely.
Do you have any predictions of where physics is going to take us next? What adventure physics is going to take us on now?
So I'm tempted to get into dark matter because, again, that was what I did my research in, my thesis in graduate school. We won't have time for it in this call, but the experimental confirmation of dark matter is a sought-after prize in the world of theoretical physics. Easier said than done, because if you have matter that's dark, it's not emitting light. You don't have electron.
And what is dark matter? Explain that to my audience.
So just to get into it briefly, dark matter is matter that is gravitationally inferred. In other words, based from its gravitational effects on the galaxy, on our galaxy, and other galaxies. We can infer its presence in what's called the galactic halo, a halo going around the galaxy. In fact, it's postulated that 95% of all matter is dark. And ordinary matter, as we know it, is only 5% of matter in the universe. However, the two do not necessarily interact very well, if at all. So while we can theoretically infer the existence of dark matter going around galaxies in a halo, so to speak, proving it experimentally is a completely different thing. For all we know, it doesn't interact with ordinary matter at all, or if it does, on a very minimal level. Because if matter is going to be dark, what does that mean? That means that you have no light being emitted. Well, if there's no light emitted, what does that mean? From high school chemistry, when light is emitted, when you have electron shifting atomic orbitals. So if there's no light emitted, you have no electron shifting atomic orbitals. That means the entire structure of dark matter is fundamentally different from the structure of regular matter. And so we don't really know what it is. All we have are candidates, structures that we suspect describe dark matter. We don't know fully what it is, but that's a conversation for another time.
Well, we'll keep a lookout for dark matter. And I really want to thank you for coming on the Nick Bryant podcast, Eric.